Welcome to the lecture series of Basic Electrical Engineering. Subject code is ECE 101. Today in this video we will discuss the topic step response of RL circuit. So RL circuit response, we are considering it as the forced source, means that we are having a voltage source in the circuit. As in the previous video I have told you that we are having the two type of circuits, means one is the forced source in which we are having the external source, and second is the natural source in which we are not having the external source, but the circuit is energized by its previously stored energy. So here we are doing the analysis of forced source when we are having the external voltage source. So here we are having the circuit in which we are having a resistance R, whose voltage across R is VR, and inductor whose voltage is VL, and here we are having a key switch. It is on when t is equals to 0, and we are having the voltage Vs, the supply voltage. Assume that the switch is closed at time t is equals to 0, and also assumed initial current in the circuit Is is equals to 0. So I0 means the initial current here. Initial current is equals to 0 at time t is equals to 0. When we connect the switch, the circuit will become as shown in this figure. It will become like the switch is closed and this is a complete circuit. The voltage source is connecting with the resistance and the inductance. So, and the current is flowing in the circuit. Apply the KVL across in this circuit at time t is equals to 0. The KVL is minus V, the voltage, this supply voltage, plus the voltage drop across the resistance, this resistance, it is RIT, plus the voltage drop across the inductor, plus L DIT by dt is equals to 0. So this is the KVL of the circuit. We will rearrange this equation into RIT plus L DIT upon dt is equals to V. Then we are taking the Laplace transform. In the previous video I have told you how we are using the Laplace transform. So here we take the Laplace transform of this equation. It will become RIS plus L. The Laplace transform of this inductance is L into S IS minus I initial, this I0 is equals to V upon S. I0 is 0 as per assumption. Here we assume that the initial current is 0. So I0 is equals to 0. So according to this condition we put it 0 and the equation will become this equation. R IS plus L S IS is equals to V upon S, and we make it common. IS 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 into R plus LS is equals to V upon S. So this is how we rearrange the equation, and we find out the equation. Is is equals to V upon S into 1 upon R plus LS. So then we make it Is is equals to V by L upon C into S plus R upon L. This is R upon L. So apply the partial fractions on this. It will become V by L upon S into S plus RL is equals to A upon S plus B upon S plus R. We will find out the partial fraction of this equation and we find the value of a and b. When we put s is equals to 0, we will get a is equals to v by r, and when we put s is equals to minus r by l, the b is minus v by r. So put the values of a and b in this equation. It will become is is equals to v by r upon s minus v by r upon s plus rl. Now take the inverse transform of this equation. It will become it. When we are taking the Laplace transform, the circuit works in the s domain. When we take the inverse Laplace transform, it works in the time domain. So it is equals to v upon r minus v upon r e raised to power r by l into t. So take v by r common, it will become v by r into 1 minus e exponential of minus r by l upon t, and r by l is our iota. So replace r by l with the iota. So it is equals to v upon r into 1 minus e raised to power minus t by iota. So this is the response of the equation. If we find out the voltage across the resistor, then it is RT is equals to IT into R. Voltage drop across the resistance is this. VRT is equals to, we put the value of this IT. So R into this is the value of IT. When we put this value, the equation will become VRT is equals to V into 1 minus e raised to power t by tau. This is the voltage drop across the resistor. So then we find the voltage drop across the inductor. We are having the two components, resistor and inductor. So voltage drop across the inductor is this. Apply the KVL. When we apply the KVL, the equation will become minus V, this V, plus the voltage drop across the resistor VR, plus the voltage drop across the inductor VL. So VLT is equals to V minus VR by T. So V minus V, we put here the value of VRT, which we find in the voltage drop of the resistance. So when we solve this, we will get this equation, and this is the voltage drop across the inductor. If we are considering the graph, this graph shows that here we are having the time domain, on this side we are having the time domain, here we are having the current, this is tau, 2 tau, then 3 tau, 4 tau, and so on, and consider time to be r by l seconds. It is tau, as we know tau is equals to L by R, and its units are in second. T is equals to V upon R. Here we put the value of tau, and we will get this equation. When we find the value of e raised to power minus, it is 0.368. When we solve this, we will get this IT is equals to 0.632 VR, means this at this at this value we will get the response, current response. So IT is equals to 63% of the steady state value. So this is shown in the graph. So this is all about the step response of the RL circuit. Hope you like this video and you understand this video. Thank you so much.